Hello everyone, I welcome back to the second video lecture on Hadoop MapReduce framework. Myself Shaman GS, working as Assistant Professor in the Department of Computer Science and Engineering, PES Institute of Technology and Management, Shivamogga. Thank you. These are the contents which we are looking today. The MapReduce model, MapReduce parallel data flow, fault tolerance and speculative execution. In that, speculative execution and Hadoop MapReduce hardware. Before we start into today's actual content, let's take a quick review of Hadoop architecture. We already know the Hadoop architecture contains Hadoop HDFS, means Hadoop distributed file system. The detailed discussion on this we had in a last lecture. Hadoop HDFS is for storing the data on various data nodes. That is, we can call it as the storage layer. In today's lecture, we are going to discuss Hadoop MapReduce. This is to process the data that is stored in the HDFS. In HDFS, the data is stored in various data nodes. That data has to be processed. For that processing of the data, we have Hadoop MapReduce. About Hadoop yarn, we will discuss in the future videos. Let us take a quick review of HDFS file system. In HDFS, no single system holds the full amount of the data. All the data is distributed over these data nodes. Here we have explained with an example, you can recall it. So processing of that data cannot occur at single location. Either we have to move the data or we have to do the processing locally. And we have already mentioned a statement that moving of the data is complicated than moving a code. Means we can move the program to every individual system where data is stored than moving the data itself. We have already discussed that HDFS is for storing the data and MapReduce is for processing the data. So MapReduce is a distributed parallel processing framework for the HDFS data. This MapReduce is meant for doing the processing of data parallelly because data is available in various data nodes. So no single data node holds the complete data. The data is being distributed over all possible nodes. Because of that, MapReduce is a distributed parallel processing framework for the HDFS data. MapReduce programming model is based on two phases. The first phase is applying a mapping process and the second one is the reducing the results. Meaning is that we have to map the process to individual data nodes, so that occurs in the mapping, and once the result is been produced in individual system or the nodes, we have to collect the data and consolidate the data. That is the second phase, reducing the result. MapReduce word is made from two words. One is mapping the process and reducing the result. MapReduce is the solution for log analytics, data analysis, recommendation engines, fraud detection and user behavior analysis. In order to understand MapReduce model, first we will do a small exercise of finding a word in a novel. This is the very old novel War and the Peace, written in Russian language, where Kutuzov is the name of the general. We are going to find out how many times the name Kutuzov is being repeated in the novel War and the Peace. For doing that, we will make use of some Unix command tools such as grep. We are already aware of the grep. Grep stands for General Regular Expression Print. We are going to find out the match case of the Kutuzov in the novel War and the Peace, and we are going to print as the output. Each match is reported as single line of the text that contains the search term. So this command is going to find out how many times Kutuzov word with leading and trailing space in the novel War and the Peace, and it is going to print as the output. So after executing this line, we are going to have series of the lines where the word Kutuzov is been found in the novel. To make the output very understandable, we are going to modify this command line. So the new command is grep Kutuzov war and peace.txt word count -l. This command is going to report the number of lines it receives. So the total output is 257 instances have been found with the word Kutuzov in the war and the peace.txt file. We have to note down that the word Kutuzov is being leading and trailing with the space. So actually we are going to find out the Kutuzov with prefix of the space and suffix of the space. That exact match is with the number 257. It is not going to find out the other type of the words, that is Kutuzov without any space or without the prefix space or without the trailing space, or the Kutuzov word with dot and comma. It is going to find out only the Kutuzov word with leading and trailing space. So in order to make the output much more clear, we are going to write two scripts in the next slide. In the above command line, the word Kutuzov is being searched in war and peace text file with the leading and trailing space. This is the exact format that the above command line is going to search in war and peace text file. There can be other format of the words with the same search word Kutuzov. For instances, the Kutuzov with dot, Kutuzov with comma, Kutuzov with only leading space but not the trailing space, Kutuzov with only trailing space but not the leading space. Such instances are neglected in earlier command line. Now we are going to do two separate scripts to enhance our search that can include these possibilities of the words. Among these two scripts, one is for the mapping script and one is for the reducing script. Now we are going to implement MapReduce model in order to find out the word Kutuzov. In this example, we identified only the one word in the whole document. Let us extend our search to two words. This is the first script, simple mapper script. Here in this script, we are going to find out the two words Kutuzov and Petersburg in the same text file. Among the two scripts, the first script is going to print the words Kutuzov, 1 and Petersburg, 1 from the whole document. The first script is not going to count the number of occurrences of Kutuzov or the Petersburg. So the first script is going to print only the partial output. It is only the instances Kutuzov, 1, Petersburg, 1. So when we complete the execution of the first script, we are going to get the series of the Kutuzov, 1 and Petersburg, 1. By taking this as the input, the second script is responsible for counting the number of instances of Kutuzov and Petersburg from the output of the first script. Let's start analyzing the first script, simple mapper script. From the whole text file, this statement is going to read the line by line. From individual line, the for statement is going to find out the individual words. If the first word, the token stands for the words in the line, the first word is equal to Kutuzov, then we are going to print out this line Kutuzov, 1. Else, if the word is Petersburg, then we are going to print out Petersburg, 1. This is the end of the if statement, and this is the end of the for loop, and this is the end of the while loop. Before we take the second script for our analysis, let's pause this video for a while and like this video and subscribe for my channel. Let's move for the analysis of the second script, the simple reducer script. From the output of the first script, the reducer script is going to find out the number of occurrences of the word Kutuzov and Petersburg. For that, we are going to initialize the variable k count equals to 0. K count is for counting the number of occurrences of Kutuzov from the earlier output, and p count is for counting the number of occurrences of Petersburg from the earlier output. So we are going to start the read line by line of the earlier output. Let me come back to the first script. The first script is going to print out the Kutuzov, 1 and Petersburg, 1. So now we got the file containing only the Kutuzov, 1 and Petersburg, 1. This is the input for our second script. So the second script is going to read the line by line output of the first script. If the line is equal to Kutuzov, then we are going to increment k count by 1. Else, if the line is Petersburg, then we are going to increment p count. And this is the end of the if statement, and this is the end of the while statement. Once we complete this, then we have the count Kutuzov, k count. K count means the number of occurrences of Kutuzov, and p count is the number of occurrences of Petersburg. We are going to print out the Kutuzov followed by number of occurrences and Petersburg, number of its occurrences. We combine the output of first two scripts. The mapper.sh is for the mapping script and reducer.sh is for the reducer script by this command line cat var and the piece.txt. This is the source file where we are going to find out the number of occurrences of Kutuzov and Petersburg using these two scripts, and we got the output Kutuzov, 315 and Petersburg, 128. This indicates that there are 315 occurrences of Kutuzov in the text file word and piece and 128 occurrences of the word Petersburg. This contradicts the earlier output. Here in the earlier output we got Kutuzov occurrences is 257, but this is a limited case where this Kutuzov is being prefixed and suffixed with the space, whereas here this Kutuzov is all the type of the instances. For example, this can be Kutuzov with prefix and suffix of the space. This can be Kutuzov with space on both sides, Kutuzov with dot, with comma, only one space at the beginning, one space at the end. So by combining all of these things, we got the output as 315. The mapper inputs a text file and outputs data in a key, value pair, that is token name, count format. The mapper and reducer functions are both defined with respect to the data structured in key, value pairs. The working of mapper function and reducer function is explained in this slide. Mapper function takes the input key 1, value 1. Key 1 may be Kutuzov or Petersburg. The value 1 is the input file, that is our text file. From that it is going to produce a list of output containing key 2. Here key 2 may be once again Kutuzov or Petersburg, and the value is the lines where the key is occurrences. So the mapper takes one pair of data with a type in one data domain and returns a list of pairs in different data domain. So this will be the input for the reducer function. The reducer function is then applied to each key value pair, the key and value pair of the output of first mapper function, which in turn produces a collection of the values in the same domain. So the reducer function takes the input which is the output of the mapper function. Key 2 may be Kutuzov or Petersburg. The list is occurrences of Kutuzov or Petersburg, and this is going to give the list of value 3. Value 3 is the actual value that is required by combining the output of mapper function and reducer function. Each reducer call produces either one value, many, or an empty response. The MapReduce framework transforms a list of key value pair into a list of values. By seeing the above examples, we can come to these conclusions. The functional nature of MapReduce has following properties. The first one is data flow is in one direction, that is map towards the reduce, not in the opposite way. New data are produced by applying the mapping and reduction functions to the input data. There is no dependency on how the mapping and reducing functions are applied to the data. The mapper and reducer data flow can be implemented in any number of ways to provide better performance. Now we will move on to our second concept, MapReduce parallel data flow. As we already know that information in HDFS is located in various data nodes, means not in a single system. It is distributed over a large number of the data nodes. So, the large amount of the data can be analyzed quickly by parallel implementation of the MapReduce. Mapper process is fully scalable and can be applied to any subset of the input data. In reducer phase, results from multiple parallel mapping functions are combined. So, parallel execution of the MapReduce requires other steps in addition to the mapper and reducer process. We will study those additional steps in the data flow model of MapReduce. This is the example of simple Hadoop MapReduce data flow for a word count program. The map process counts the words in the split and the reduce process calculates the total of each word. So input is the text file. This text file contains, let us assume, 3 lines. Each line contains 3 words. So in order to find out how many times the individual word has repeated, we have to split the input into the number of lines. So 3 line input will be splitted into 3 separate lines here in the split part. So the first line contains C spot run, the second line contains run spot run, the third line contains C the cat. The next step is mapping. Here we are going to assign the key value pair. Key value means C is the key and the value is 1. Why it is 1? Because the C is been repeated one time. Similarly, spot is the key, the value is 1. The run is the key and the value is 1. In the second line, run is the key, 1 is the value. Spot is the key, 1 is the value. One more, run is the key and 1 is the value. Similarly for the third line. So this happens in the mapping phase. In the shuffle phase, individual words of any mapper will be collected. For example, we have to consider all the mappers in the mapping phase to collect the individual words. All the C words will come into this block. Similarly, all the spot words will come into this block. All the run words will come into this block. All the words will come into this block. Similarly, all the cat words will come into this block. Individual block indicates one word and number of times they are repeated. C is been repeated 2 times, spot is been repeated 2 times, run is been repeated 3 times, the repeated by 1 time, cat repeated by 1. In the reduce, these number of occurrences of individual words will be collected and reduced to the value. So the C is the key and here the value is 1 and 1 because there are the 2 times it is repeated and now it is been converted into 2. The number of times the word is been repeated. Spot, 2, run, 3, the, 1, cat, 1. For example, run is the key and the value is 3. This indicates the key run is been repeated by 3 times. And in the output phase, all of these reduced outputs will be collected and this will be the final output. Individual phases of MapReduce word count data flow is explained in the subsequent slides. Let us start with the input. In this phase, HDFS distributes and replicates data over multiple servers. 500 MB file broken into 8 blocks and written into different machines in the cluster. Data are also replicated on multiple machines, usually 3 machines. The input split used by MapReduce are logical boundaries based on the input data. For example, the split size can be based on the number of records in the file or on actual size in bytes. Splits are almost always smaller than the HDFS block size. The number of splits corresponds to the number of mapping process or the mappers used in the map stage. In the map step, for large amount of the data, many mappers will be operating at the same time. User provides specific mapping process. Mappers will be executed on the machines where the block resides. Since the file is replicated in the HDFS, the least busy node with the data will be chosen. If all the nodes containing the data are busy, MapReduce will try to pick the node that is closest to the node that hosts the data block. The last choice is any node in the cluster that has access to the HDFS. The next step is combiner step, and it is an optional stage. Whenever we get the same words repeated, then this step will be involved. In this step, it is possible to provide optimization or pre-reduction as a part of the map stage, where key value pairs are combined prior to the next stage. This stage will help the next stage in combining the repeated words at the mapping stage itself. Let's go to the next step. Shuffle step. All similar keys must be combined and counted by the same reducer process before the parallel reduction stage completes. Results of the map stage must be collected by key value pairs and shuffled to the same reducer process. If only a single reducer process is used, this step is not needed. The last stage is the reducer step. As per programmer's design, reduction is being performed. The results are written to the HDFS. Each reducer will write an output file. For example, 4 reducers will create the files called as the part 0000, 0001, 0002 and 0003. Meaning is that individual reducer will create an output file. Reducer phase produces individual outputs, and the output phase will combine all these outputs to make it as a single output file. So far now we have seen MapReduce data flow model, where we have seen 6 different stages of the data flow. Now we shall see how these things are actually executed in the process placement during the MapReduce. Hadoop Yarn Resource Manager and the MapReduce framework determine the actual placement of the mappers and reducers. The MapReduce framework will try to place the map task as close to the data as possible. It will request the placement of the yarn scheduler but may not get the best placement due to the load on the cluster. This diagram shows a simple 3-node MapReduce process. Once the mapping is complete, the same node begin the reduce process. The shuffle stage makes sure the necessary data are sent to the each mapper. Also note that there is no requirement that all the mappers completes at the same time, or that the mappers on the specific node be complete before the reducer is started. Reducer can be set to start shuffling based on a threshold of percentage of mappers that have finished. Here we can see that there are the 3 nodes meant for mapping process and as well as the reducing process. In the mapping process, the preloaded local input data, which means that the node 1 contains its own local data. On that data, the mapping process will happen. Similarly, the node 2 will contain its own set of the local data. On the basis of that data, some mapping will happen. Similarly for node 3 also. Once the mapping of all the 3 nodes is been completed, the same nodes, node 1, 2, 3 will share the data to start the reducing process. Here we are not supposed to confuse that these nodes, node 1, 2, 3 are different than node 1, 2, 3. They are not different. They are the same nodes. Once the mapping is been completed, the same nodes will exchange the data to start the reducing process. Okay, this is the same node. Node 1 is same as this node 1. Node 2 is same as this node 2. Node 3 is same as this node 3. Once the mapping process of all the three nodes is been completed, they will exchange the data. Means that the data from node 1 will be sent to the 2 and as well as 3. The data from node 2, the data means the processed data is been shared to the node 1 and node 3. The data of node 3 is shared to the node 1 and node 2, and they can start the reducing process. And once the reducing process is been completed, the outputs are stored locally. This blue color indicates the output of the input data that is stored locally. So ultimately the local data is been mapped, exchanged to other nodes in the reduction process, and once again the output is stored locally. Steps happening in this diagram are summarized here. It shows simple 3-node MapReduce process, meaning is that 3 nodes are been taken into our example. Once the mapping is complete, same node begin the reduce process. Shuffle stage makes sure that necessary data are sent to each mapper. It's not necessary that all the mappers has to complete at same time. Reducers can be set to start shuffling based on a threshold percentage of mappers that have finished. Now we shall move on to our last topic, fault tolerance and speculative execution. One of the most interesting aspects of the parallel MapReduce operation is the strict control of data flow throughout the execution of the program. For example, the mapper process do not exchange the data with other mapper process. The design of the MapReduce make it possible to easily recover from the failure of the one or many map process. For example, should a server fail, map tasks that were running on the machine could easily restarted on another working server because there is no dependencies on any of the map tasks. The confined data flow enables MapReduce to operate in a fault tolerance fashion. Easy recovery from the failure of one or more map process, no dependencies on any other map task. In functional language terms, the map task do not share state with other mappers. The application will obviously run slowly because work need to be redone, but it will complete. Even failure of reducers can be restarted. If a reducer task has to be completed on down node, the MapReduce application will need to restart the reducer task. If the mapper output is not available for newly started reducer, then these tasks will need to be restarted. This process is transparent to the user and it provides fault tolerant system to run applications. One of the challenges with many large clusters is the inability to predict or manage unexpected system bottlenecks or failures. It is possible to control and monitor resources so that network traffic and process load can be evenly balanced. In practice, however, this problem represents a difficult challenge for large systems. When one part of the MapReduce process runs slowly, it slows down the everything because application cannot complete until all processes are finished. Nature of parallel MapReduce model provides a solution to this problem. We know that input data are immutable in MapReduce process, so it is possible to start a copy of running map process without disturbing other running mapping process. For example, most of the map process are coming to end and the application master notice that some are still running. So it schedules redundant copies of the remaining jobs on less busy or free servers. The secondary process might finish first and so the other first process are terminated and vice versa. This process is known as the speculative execution. The same process can be applied to reducer process that seems to taking long time. Speculative execution can reduce cluster efficiency because redundant resources are assigned to applications that seem to have slow spot. It can also be turned off and on in the MapReduce site.xml configuration file. Now we move on to our last topic, Hadoop MapReduce hardware. The capability of the Hadoop MapReduce and HDFS to tolerate server or even whole rack failure can influence hardware designs. The use of the commodity servers. Commodity servers means the lower end systems. The use of the commodity servers for Hadoop clusters has made low cost, high availability implementations of Hadoop possible for many data centers. The use of the server nodes for both storage HDFS and processing mappers reducers is somewhat different from the traditional separation of two tasks in data center. It is possible to build Hadoop systems and separate the roles, discrete storage and processing nodes. But majority of the Hadoop systems use general approach where servers can act both roles. Another feature of dynamic MapReduce execution is the capability to tolerate dissimilar servers. That is, the old and the new hardware can be used together. Dear friends, this is all about Hadoop MapReduce framework. In the next video, we will discuss MapReduce programming. Thank you.